What were you looking at to go through and say C? What about the dashes and the wedges?
They would like essentially flip. So instead of if one of them is dashed, the other one would be dashed for the other.
What are enantiomers? So fantastic. And I'll talk through that again. So mirror image. If I take the mirror image of CH4, I'll be literal on it. Right? CH4, right, which would ultimately mean CH4, is the relationship between the red and the blue enantiomers. Right. Well, that's a formula. We're supposed to do it with structures. Okay, structures. Blue dot will be my mirror. Reflect through my mirror. I get that, right? Are they mirror images? Yeah. Are they enantiomers? No. Because when we're talking about enantiomers, it's a two-pronged definition. Non-superimposable mirror images. Right? So CH4 is superimposable on its mirror image, which means the relationship between the green and the red ones are what? They're identical. Okay? So not mirror images, not enantiomers. Right? And then what you were suggesting was a really, really good idea. When we're going through and looking for these enantiomers, what we're trying to consider is how the things changed. Right? And so your first approach was that if you were going to look through a mirror, and this is going to get a bit strange. Let's see. Can I pull this off? Why not? Right? Let's put a mirror in front of the molecule. Right? That CH3 is coming up at us, right? And if I put a mirror here, where would it be? Be right there, right? Is that CH3 now coming at you or away from you? Away. So if you're reflecting through that mirror image, what happens to your wedges and dashes? They're going to flip. So you could go through and say, well, the mirror image for this compound, the backbone of the structure doesn't change, but I would expect all of those positions to change. What was dashed is going to become, I already zoomed out of it, was wedged. And so you're like, oh, C, okay, and as your statement for C, because dash CH3, we're maintaining everything in the exact alignment. Nothing spin, flip, or rotating. Maintaining because we're looking at the mirror image directly in front of the molecule. Okay. CH3 reflected. Makes sense. The OH didn't reflect. And the bromine, oh wait, I looked at the wrong structure. Sorry. The OH, God, stop looking at the answer, Mike. CH3 reflected. The OH reflected. The bromine did not. Okay? If it was going to be that perfect mirror image, it has to have all of them reflect. One part did not reflect. Okay? So C looks really, really close, except that last piece did not. Which means, are they mirror images? No. What are they? Okay? They're diastereomers. How do we know they're diastereomers? Okay? Some of it can go back to they're not enantiomers. But then let's try this. Bear with me a second. I think I did that right. Did I do what I wanted to do?
Yeah. So if you mirror that and then flip it, it'd be C.
Oh my good God.
What is going on with my brain today?
Not the answer.
What's that? It happened to you too?
Wait, for C? If that was an option, it would be the answer.
Oh, of course, all of these things were in the way too. Forgot about all that. God, what day is it? Too many pieces. If we take a look at the structure that I just drew, what was my fucking question?
I think you're asking what it does.
I think that's where I wanted to get, because your diastereomer was, your definition was not an enantiomer. Is this structure an enantiomer?
Of A or C?
Of A.
Of A, okay. Of the original?
Yep. Is that an enantiomer?
Yeah. Oh, no. I mean, wait, you could flip it, right?
Okay, so now what we're starting to get is some people being like, where's going on? And you're in the same brain wavelength as I am right now, and I apologize for that. Hopefully you should get off of my wavelength and get on a better one. Okay? But other people are like, they started to move their hands a little bit. Because what you're talking about doing is how do you manipulate that molecule? Okay? Is this one an enantiomer? No. Does that make it a diastereomer? Because that was the definition you just gave me, right? If it's not an enantiomer, it must be a diastereomer. And you're saying no. Why not?
That's identical.
Wait, this structure is identical to the one that I drew up there?
Yeah.
Do you see that it's identical? For those people that have already said yeah and are shaking your head yes, you knock it off. The rest of the other people, they're looking at it. Do you see that that black structure that I drew is identical to the original drawing? Okay? And if you're now starting to gesture, you just flip the molecule. Yeah, that was exactly what I was trying to do. I was trying to break that definition. I'm back on my wavelength, the correct one. The definition of, well, they're not enantiomers, so they must be diastereomers. Okay? Because that definition is flawed, because it could be identical. Okay? There could be an other relationship. So I know where you're trying to go with, well, if they aren't enantiomers, they must be diastereomers. That's having moved through the flow chart to get to that point. Moving through that flow chart means you had a whole hell of a lot of other questions that you had to answer. Okay? So you've got to be careful in listening to people's statements of, well, if they're not enantiomers, they're diastereomers, because they've done a bunch of extra work that you may not realize they've done. Does that help make sense? Does everybody see that the structure that I've drawn at the bottom is identical to the top one? Are we good with that? Okay. Cool. So when we go back to that initial assessment of trying to find the enantiomer for our following compound, okay, if we reflect it across, we're seeing those exchange. Okay? Do they have to exchange, though? Okay, so C, we just said, didn't work, and we are correct in concluding that they're diastereomers. One part of your structure did not reflect. But do we have to reflect? Do we have to change all the wedges to dashes and the dashes to wedges? Okay, some people are like, actively, yeah. What happens if I put a mirror right here?
They still say the same, like dashes and wedges.
They're going to stay the same. Dashes and wedges. Okay? Except where would my OH be drawn? On the right or the left of my molecule? On the left, because of this molecule presence of where that mirror image is, there's my OH. There's my wedged CH3. There's my wedged, sorry, it's not wedged. Now we got a structure underneath it. My dashed bromine. Did I exchange wedges for dashes?
Not yet.
No. It's not even that, not yet. Are these now mirror images? Are they non-superimposable? Okay, and that becomes the hard one. How do you figure out if they're non-superimposable? Okay, and flip becomes a fun word too. But what we want to try and do is manipulate this structure so we can see if they overlap or not. The hexagon overlaps perfectly. Everybody see that? Okay, but the substituents wouldn't flip or wouldn't align perfectly at all. So one option was suggested is to take that drawing and flip it over. Okay, so we're going along this axis and we want to flip. That's not the axis you wanted to flip on, is it? Casey? Yeah, sorry. That was the axis you wanted to flip on. What's going to happen to the hexagon background? It's going to stay the same because it's just flipping over on that axis. Okay? What happens to the bromine? Well, the bromine was aimed away from you, and then what did you do? So now the bromine is wedged coming at you. Whoops. But not only is it wedged coming at you, which side of the molecule is it on? It's on the other side of the molecule. Okay. What happened to the OH? Okay. It started away. We do the flip and it becomes coming at you. What happened to the CH3? Started at you. We do the flip. It's going away. What's the relationship between these two molecules or those two drawings? Those two drawings are identical. Okay? So now what we could go through and do is start to say, well, are they non-superimposable? So we can now take our new flipped structure, slide the hexagon across, hexagon overlaps. CH3 is up, that's great. Okay, is it wedged or dashed? One of each, do they overlap? No, what happened to the OH? Do they overlap? Bromine? No, they don't overlap either. So what does that do for us? What have we now generated? What have we drawn?
To answer.
We've drawn the enantiomer of that question. So now all we have to do, okay, and in fact, not only did we draw the enantiomer, we drew two versions of it. Okay? And we could take either of those two versions and now try and match it to any of our answer choices. Kind of, sort of? Is it right there? No, it's not right there. Okay? So it's not D, because we got the CH3. We're looking at them on the left-hand side. The CH3 should be wedged and the OH should be dashed. So that didn't work. The bromine should be dashed and the bromine's dashed. So what's the relationship? Diastereomers. Take a look at answer choice A. What's going on with answer choice A? Okay, we did another permutation on the molecule. So let's hold our horses, because do we want to do more permutations? Ideally not. Okay, particularly if that more permutation is for the wrong answer. Okay, so before we do that, let's go through and see what answer choice B is. And of course, answer choice B also shows a permutation. Does that make sense? So what we want to try and do is now take our drawing that we spent all this time to ensure was the enantiomer, right? That's the structure that we had up here. Right? And we want to see what it matches with. Okay? Answer choice A and B did a secondary permutation. So what do I want to do? I want to flip this molecule. The axis I want to flip on is running through there. What happens to the hexagon?
It stays the same.
Stays the same, is perfectly acceptable as an answer. As I do that flip, what happens to the OH?
It switches a wedge.
Right.
Instead of being dashed, it's solid.
It's now going to be a wedge coming at you. What happens to the bromine? It should be wedged. Where? On top. What should be the CH3? Now I can take this flip that I did with my structure and compare them to those answers. And what do I see? B comes into alignment. Which means? Say again? B is the answer. We started the question with, I don't want to look at the answer choices. You've got wedges and dashes on 3 different sites. Depending on how we decide to organize those, just those 3 different sites, permutations is 2 to the 3rd. That's 8 different answer choices. Consider the fact that we could flip the molecule over, which we did. That's now 16 different answer choices. Okay? We didn't even talk about, how about let's just rotate it in the plane. Okay? So it's going to be real easy to lose track of your wedges and we already saw, I did. Complete brain meltdown 10 minutes ago. Felt like 10 minutes ago. Okay? So what we did was drew the mirror image, verified it was non-superimposable, so we were happy with that. And then we started to say, with that mirror image, does it look like my answer choices? Can I start to weed out answer choices? Yes, I can. Yes, I can. Ah, crap. They did a flip on me. What does that mean I got to do? I'm going to do a flip. Okay? If I'm in a spot where I have to do that flip. Now that I've done the flip, I can now clearly align it to my answer choice. Does that make sense? Do you see the amount of work and processing that comes into this? How many of these questions do you expect to see on the test?
2.
Okay. 1, maybe 2. Seems reasonable. Okay. Not 38. Okay. Remember, we build slowly. We'll target each of those individual pieces. Kind of make sense? Chirality as an area is very challenging to manipulate because we're trying to deal with 2-dimensional drawings representing a 3-dimensional world, and our 3-dimensional world can flip wherever the hell it wants, and we have to pick the one correct orientation that matches both the answer choices and our brain's understanding of it. That's a lot of processing power. When do you think you should answer this question on the test?
First or last?
Okay. Why would you say first?
Yeah.
Okay. If you really know it, okay, that's a fair assessment. I could go with that. Okay. For me personally, I think I know it pretty darn well. It's going to be the last question I answer. The odds of me making a mistake, through the flippin' roof. Just because I know it, I also know that I'm going to screw it up. Okay? So I'm not going to spend a bunch of time working on this when my brain is fresh, because more than likely, even if my brain is fresh, I'm going to get it wrong. So let's just wait to the end, draw out as much work as I can get, and try and get that answer right. And instead, focus on other questions, like what things are in the nucleus. Okay? Because that question I have an increased odds of getting correct and making fewer mistakes on. Okay? A triaging process. That requires that you're reviewing through the exam. So you've spent the beginning of the exam getting an idea of where questions are at, okay, and where your questions are at. Your questions are the ones that you have mastered and you think you've owned that content. Focus on those. You do not have time to master everything. You will get something wrong. Okay? This is where it pushes to what you know. Focus on what you know, get those addressed, then you can move to the things you don't know. But don't sit and spin on something like this that's going to break you. Make sense? Whose question was that? Oh, that was you. God damn it. Does that help? Okay. We could push on this question and make it a little bit more challenging. Okay, for the sake of just what are we working with here? Identify the relationships. We already picked B as an enantiomer. So spend some time. Prove to yourself what's going on with red, orange, and green. So we compare A to the starting material. What's the relationship between those two drawings? Okay. C to the starting material. What's the relationship between those two drawings? D, what's the relationship between those two drawings? So what you're trying to do is test yourself for all the wrong answers. You might be like, well, that's dumb. Why do I want to test myself for the wrong answers? Because no instructor has an infinite amount of time, and they will almost always write test questions based off of stuff they already have at hand. And I could easily switch this question from which of the following is the enantiomer to which of the following is identical. Maybe the diastereomer. I don't think I can ask the diastereomer one on this one. Because I think a bunch of them are diastereomers. Okay? But what you're trying to do is find those relationships and pick up speed with that practice. Does that make sense? Okay. Spend some time. If we look at answer choice D, that red arrow, if we just rotate about that axis. Okay? So that means the CH3 that was wedged, rotate around, is going to become dashed, but now instead of being above the structure, it's going to be below the structure. So we should see it down here. The bromine that was dashed below, as we do that flip, close enough, I should go above the structure and now towards us. And so that would be that answer, okay, or that description of that permutation. We could then take that back up to our parent structure and say, okay, well, what's the relationship? We could go through and note, well, the OH looks like it could be a mirror image, but then the bromine and the CH3 are in the wrong spot. Okay, so what you might go through and do is then say, well, I want to do another flip. But if you're doing another flip, you're just going to take it right back to structure D, okay, which was an interesting statement. Okay. The other idea that you could go through and do would be maybe take the structure and flip it on this axis. Okay. So now all those substituents that are on the left of that line will move to the right of the line. And the question becomes, where are they located? Well, the bromine started dashed is now going to become wedged. The OH was wedged, so it'll become dashed as we do this flip. The CH3 was wedged, whoops. So it would become dashed. Okay. Is that easier for you to see the relationship back to the parent? If yes, you found the permutation that works for you. And that, I think, becomes one of the most challenging things within the system, is what permutation, what spin, flip, or rotation was done that allows you to find the relationship as fast as possible. That will be different for almost everybody. Okay? And until you go through and do enough practice to manipulate these structures, it's going to be slow. Kind of, sort of. Okay, so what is the relationship if we go top to our bottom right? The OH superimposes, the bromine does not, the CH3 does not. So they're not superimposable, okay? And if it superimposes, they aren't mirror images of each other either, which means they're diastereomers, okay? And since you don't have to talk through it, don't worry about talking through it. You won't have an answer that is it A, diastereomers, B, disastomers, is it C, dinosaurs? Like, just pick the D one, you're fine. Okay, does that make sense? Should we go through the other ones?
Yes.
So let's get rid of other ones. I guess it's just one more. Two more. What's going on with the orange one? Okay, and again, it's going to come down to what you see and where you see it, when you see it, all of those potential things. Okay. Do they superimpose? No. At least are all the substituents in the right quote-unquote place, two-dimensional place. The CH3 is above, the bromine is down below. If I slide them up, that all aligns. So they are in the correct flat space. Okay? But now the three-dimensional world is a little bit confused. For me, I like to see mirror images over here. So what I want to do is I want to take my orange structure and I want to align it such that I could get it up into that potential mirror image spot. So the first thing that I would do would be flip this structure. Because I'm flipping it on that axis, that OH becomes dashed. What happens to the CH3? Becomes wedged. What happens to the bromine? Okay. And now what I'm doing in my head is sliding that orange structure up where that mirror image should be and be like, are they mirror images? No. So they're not mirror images. Okay. Were they superimposable? We'd already tested the superimposability right out of the gate. They weren't superimposable from the beginning. Okay. Which means diastereomers.
We also need this too, like if you look at the OH and BR with the chiral atoms.
So could you also go through and run, I think what you were saying was from the original structure?
Yes.
Could you look, whoops, trying to make it more simple. Could you just go through and look at your original structure and say, well, what happened at each of those spots? Well, the CH3 mirrored, the OH mirrored, the bromine did not. So they can't be enantiomers, right? Because the connectivity is all the same and they're still non-superimposable. I could go through and call them diastereomers. Is that easier for you? Then do it, okay? And so that becomes kind of the challenge here, is that there's multiple paths to get to the same place. Which place is easier for you to navigate consistently? Okay? You will find that through practice. Because I'll tell you what you just described, I think is brilliant. Nope, not through my head. Not at all. What would I do? I'd do all the drawing stuff. It would take me half an hour, but I'd do all the drawing stuff and be like, oh, this is the relationship. Right? Because that rule thing just does not stick in my brain, so I can't do it that way. Okay? Classically, when I talk about chirality, it is one of my least favorite areas to talk about because my brain does a very poor job of holding on to those objects and manipulating them in the three-dimensional space. Okay? I can do it, but I can do it because I've now had 20 plus years of practice doing it. Right? But if we go all the way back to OChem 1, I didn't have that practice. The only thing that I could do would be redraw the structures because I could trust that. I did not trust myself with the definitions of, I just flipped this thing around. Okay? So you have to decide where you trust yourself and your abilities. Is that bad? I don't trust myself? Feels kind of bad. Does that make sense? Do we want to look at the red one too? Yeah. So the first thing that I would do would be just try and slide it up into the blue, because that looks like it would almost mirror across perfectly. Except, what's the except? The bromine in the CH3 would be in the wrong spot. So what does that mean I'm going to do? Okay, I'm going to rotate on that. That was a weird looking one. The OH was dashed, which means it's now wedged. Okay, because I'm flipping on that axis, the CH3 that was wedged coming at me from the bottom, I'm now flipping up top, but it's now going to be aimed dashed away from me. And that bromine that was dashed going away, when I continue that flip around, is now going to be aimed at me. Now I would slide that up into that mirror image system and say, are they mirror images? No, they don't fit the mirror image definition. Okay. Are they superimposable? Okay. That again becomes a hard one. Where would I go with that one to figure out my superimposability? Yes, I'm going to erase that work. The superimposability for me, I've got the OH on the left-hand side of the molecule. I need it on the right-hand side of the molecule. It's dashed, it's dashed. Those are good. I want them to be dashed. What am I going to do? Plane of the paper, rotate. If I'm going in the plane of the paper to rotate, the OH is still going to be dashed. What happens to the CH3? I didn't hear an answer. What happens to CH3? Just taking that structure in the plane of the paper and I'm just turning this. Okay. So there's my CH3 coming at me and all I'm doing is rotating. It's still going to be coming at me, but the extra piece that I need, not just that it's wedged, and that it's on the high end. What happens to my bromine? Still going to be dashed, but now it's going to be on the low end. What was it? Bromine. Why did I want to do that? Now what can I do? Ooh, I can superimpose it directly. Could I have done that permutation with the red structure also? Yeah. Was that easy for me? No, I found it easier to rotate the original. Are both going to lead to the same answer? Yeah. It's going to come down to which permutation you find personally easier to navigate. Make sense? So what's the relationship? Identical. Kind of, sort of? Okay. Why talk about chirality at all? I'm not positive it's actually stated in the lectures. I know it's stated in the model activity if you read all the words. If you didn't read all the words in the model activity, you may not have seen the reason why it's important. Right? Yeah?
But there isn't a fixed, like, up and down and left and right in molecular.
Yeah? There's no up, down, left, or right. Yeah.
Yeah.
Watch out for the hole.
So this helps us orientate molecules.
So it could help us orient the molecules. I would argue it's more important than that.
Is it what you were saying about
Nope. Because all of that is still kind of, I would argue, almost philosophical. Like, oh yeah, we should do it because it's important, because yay, OChem. But none of you are like, yay, OChem. So I think that explanation's a little bit pandering. What was the point of OChem? To make molecules. Well, why are we making molecules? To make drugs that mess with your brain so you could see new dimensions. Welcome to the 60s in organic chemistry. Okay? Look it up. Okay? But that's now making things that mess with your body chemistry. Well, your body has tons of chiral things in it. And if you go through and ingest a drug that also has chiral things in it, they don't play the same. Okay? Anybody left-handed in here? Cool. How do you like scissors?
I make it work.
Yeah. Okay? If you know a left-handed person, ask them about scissors. They're usually pretty... That was a nice way of saying it. They're usually
Yeah,
a
but
little...
I go slow. And then sometimes I have to actually use my right hand.
Yeah. Because scissors, guess what? Are chiral. They're built for right-handed people. Right? And if you use your right hand with them, you're like, oh, this is easy. What's the problem? Okay, use your left hand with them, and then you feel like a 2-year-old with scissors, and it becomes really challenging to navigate it, and it hurts, okay? Because that's two chiral things interacting, okay, from different states. Your hands are chiral. If your body is chiral and we now inject drugs into your body to interact with any of those particular sites, it's going to interact differently. Okay, ibuprofen. Do we have any pharmacists? Yeah? There's another name usually associated with ibuprofen. It's not just ibuprofen. Maybe I'm thinking of the wrong word. I think I'm thinking of naproxen. What's usually associated on naproxen? You'll probably see plus naproxen or minus naproxen. Why? It's chiral. And in fact, you're not going to see both of those because naproxen, and I don't remember which one's which, the plus form is an NSAID. Yeah, great. Heals your pain and all that fun stuff. Heals your pain. Masks your pain. Okay? The minus one causes more pain by destroying your liver. And all that happened is you change the orientation of one atom relative to the other atoms. And you go from a drug that, yeah, I don't feel the pain anymore, to, oh my God, I need a new liver. That's kind of a big deal because of how the molecule is processed in the body, which is chiral. It changes the activity of the drug significantly. Sometimes it doesn't matter. The body only sees the positive form and the negative form is like, whatever. And if that's the case, what do all of our drug companies go through and make? They don't care. They make the plus and minus and they give you a dose. Okay? And they're like, oh, you just need to take 4 of these 500 milligram tablets. You're like, okay, great. Okay? But if they'd purified it, you would have only needed to take 2. You're doubling the dosage because half of your dosage is useless. Okay? Why would they do that? Well, what we'll learn about when we start actually talking about chemical reactions is it can be really hard to make one pure versus not. Okay? So what we effectively discovered, I believe in the 1950s, with thalidomide is that this was a big deal. Okay? Chirality was first discovered by Fischer playing with wine. Yeah. Okay, playing with wine. And we're like, oh, cool, look, it makes light spin different directions. Like, who cares about that? What a fun party trick. And they were like, not a big deal. And we gave women drugs. And instead of curing their morning sickness, we also introduced a whole bunch of mutations into their unborn fetuses. Because one of the forms turned out to be a mutagen, and the other form cured morning sickness. And we never bothered to purify them because we're like, oh, how big of a deal can it be? It's kind of a big deal. That's why you now get to study it. Okay? And you already have the reasons for why we wanted to ignore it. It's hard. I don't want to have to think like that. I hope it doesn't matter. Hope's a bad idea. Well, that's overstated. Okay? We should test these things before we just throw drugs at people. So that's why we have to deal with it. Kind of make sense? So what next?
The 1,3 diaxial.
1,3 diaxial. Okay, because you're super happy with drawings. Let's go ahead and draw a chair. And if we draw a chair, more or less, it's a little bit up there, but you know. Okay, we can put an axial position on it. We'll call that carbon position 1, 2, 3, and we want another axial position. And note which way are your axial positions pointing? They're both pointing up. So up or down. It's not up or down. They're both pointing up when I talk about the 1, 3. But maybe that's because I counted the wrong direction. Maybe we should have counted the other way. 1, 2, 3. And I look at that axial. Where is it? Also pointed straight up. So you did make an observation, which was really good. The emphasis was a little weird there. Okay. We do have down axials as well. Okay, so they do alternate around. But when we're talking very specifically about the diaxial, what we're referring to is a 1,3 diaxial interaction. Why? If those groups are aimed up, these groups can talk to each other. Okay? And that talk to each other, oh yeah, we like talking to each other. Not quite a good talk to each other. The electrons on one of those groups can butt against the electrons of the other group, can butt against the electrons of the other group. And what happens when electrons get near each other? They repel away. So that 1,3 diaxial interaction is a destabilizing interaction. What it's saying is that the structure that we're looking at here does not like being in this position. So what's going to happen? These atoms will all rotate away from each other. Well, what happens if they rotate away from each other?
Flip the chair.
All that ends up happening, stop it, pen, is you flip the chair. Okay? And in flipping the chair, what ends up happening?
Now they're all.
Those three positions that were all axial are now all equatorial. Was that obvious with my drawing? What's that?
No.
Of course you would say that.
Yes.
So, for the sake of the recording at home, that's why we drew all those. Because the recording at home doesn't, apparently you don't either, doesn't get the potential benefit of pulling out a model kit. And if we've got a model kit, what we can go through and do, oops, don't use your teeth, Mike. Is we can visually pick this up with the model kit. Gets a little bit challenging, particularly because the kit that I've got here is small. So number one, okay, we're gonna just make this 2 methyls instead of 3. So number one, okay, ignore the 2 things on top. Everybody see what those 2 things are? Pretend they are not there. And just look down here. Okay, ideally what you would see is 1, 2, 3, 4 atoms. Everybody kind of see that shape? That shape is our chair, or what we call a chair. Okay? Other people call it like a recliner, right? You're sitting in or a lounge chair. Okay? That is our chair configuration. If we sat in this chair, right, it's going to face, whoops, I aimed it for me, sorry. If I sat in this chair, I would be facing this direction. So that matches the chair above me, I think. more or less. Everybody happy with that? Okay. What's going on with these axials? So here's two of those axials, and as I turn those bonds, what do we end up hearing? A collision. That's electrons colliding with electrons. Do electrons like other electrons? No. Okay, so that's a destabilizing feature. So what those are going to try and do is they're going to, and it would be really nice if it all worked perfectly with me, it's not going to, but I'm going to try it anyway, that they're going to repel away from each other. As they repel away from each other, oh, just do it. I know you want to. And there was one up here that also wanted to rotate that way away from it too. And what just happened to the methyls? They're now not up and down above, they're now whooshed out to the sides. Okay? And if we push on that chair, I didn't do a very good job holding on to where my chair was. Come on. Everybody's watching me. Which way did my chair face? Yeah. Right? Chair's facing that way. Everybody see that? Still facing that way? Okay? But as we flip that, now where's my chair facing? Hopefully what you can see is the chair faces the other direction. It's facing the other direction. And now those groups are spun out to the side. And what happens when I rotate those? What do we hear? We hear no collisions. Because putting the groups out to the side put them in a space away from other electrons. That's a lower energy state. This is effectively Newman projection conversations, because in Newman, we wanted our electrons to have as much space as possible. That's what's happening here. So the 1,3 diaxial interaction is yet another way to look at a destabilizing force of the axial positions that forces our cyclohexanes to adopt those substituents into the equatorial positions. And that's why we reference them as axial and equatorial. Was this your question? Okay. Because I lost track of that. I wanted to make sure I got it. Does that help make sense? Yes, sir.
We look at smart work 4, or chapter 4. It was sort of about this.
Yes.
It was like methyl groups attached. It was
Yes. I think I know what you're talking about, and then, yeah, it's a fun one. More than likely, it's the same one you're talking about. Before I do that, I just wanted to mention the 1,3 diaxials are also called something else typically. Because it's like these things, right? Come on. That are like standing up out of the ground and just like showing off how cool they are. Kind of like flags.
those are called flags.
It can be referred to as a flagpole interaction because these are the poles standing up and our groups are the flags hitting each other. It wasn't that much of a stretch, but that is what it's called.
Angles, okay.
Because the flagpole was any better than the chair?
That looks like a chair.
Okay. Well, you got me then. We pulling your homework?
Sure. I think it was 9.
Why do you care? Probably want to get it right. I'm going to bet 8. What? Why are you swearing now? Do you just get it now?
It was 8 instead of 9.
Okay.
Yeah.
Wow, that was a lot of anger for.
What is it?
So, how many Gaussian interactions are present in the most stable chair conformation of 1,2 trimethyl cyclohexane? Okay, so we're going to approach this a couple different ways. The model kit is by far going to come in more handy. So if you've got a model kit, this is probably a good one to build a model for. Though I'll also add you could thank Andrew because I believe this is not a grouped question. As in, if you haven't seen this question yet, you will now have the answer.
Yeah. Or it should have been done, right?
Okay. Oops. Officially, it's not due until next week, right? Yeah. So we're looking at cyclohexane. My approach, I would immediately draw out a cyclohexane. Note I'm drawing it small because this isn't the overhead. The overhead view isn't what we actually want for this. Okay? And I have a 1, 1, 2 trimethyl cyclohexane. I could go through and show the CH3s, but as long as I've got it defined this way, I should be okay. And now it's also asking for the most stable chair conformation and, more importantly, the Gauss interactions. Right? I'm drawing it this way for me so that I know the context of what my drawing or my structure should end up looking like. Okay? I know I need to convert it into a chair, so I'm just going to pick a chair. And I'm going to draw my chair and see what happens. Okay? I want to go through and now match these 3 methyl groups to the carbons of my chair. I can number it from wherever I want. I will express that my default is to call that, well, that should be number 1, but I would call that point number 1. I know this is reading backwards, but that one by far is the easiest for me. Okay, this would be our head. I can't write it right there because I got to draw stuff there. That's my head of the chair that I'm going to define as position 1. Okay, I'm going to count my overhead view clockwise. So 2, 3, 4, 5, 6. If I go back to my chair, I'm going to continue that clockwise pattern all the way around. How big a deal is that? Not a huge issue right now, but it can become really important, say, if we moved into the concept of chirality. Okay? And you're being asked to find those relationships, it's going to become really, 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 really critically important to actually number correctly, clockwise versus counterclockwise. You got to be consistent. Okay? So at position 1, I have 2 methyls. Okay? I have to draw both, so I'm just going to draw one straight up as axial, and I'm going to draw the second one as equatorial. Okay? I had to put 2 on there, so I'm going to go with that. I also have position 2. Position 2, I have a methyl. Should I put it axial or should I put it equatorial?
Equatorial?
Okay, why should I put it equatorial? So what we just talked through with the diaxials at a minimum is the axial position creates a diaxial or flagpole interaction that's high energy. What does the question ask for?
Lowest.
Most stable. What's another word for most stable? Yes, now, Andrew.
Lowest.
Lowest
Lowest
energy.
energy.
Okay? So that means if I'm going to drop in my next methyl, given the choice between axial and equatorial, I'm going to put it equatorial. That's going to be more stable. Okay? I've now got a proper chair. So far, so good? Okay. It then asks for Gauss interactions. What the heck are Gauss interactions in reference to? These are Newman projections. Is a chair a Newman projection? If you look at it in the proper angle, everything's a Newman projection. Therein lies the problem. So what we would then want to do is shift our focus so that we could get into a Newman projection. Okay, so we're ready for some fun? That's not the optimism I wanted to hear. Is that going to delete my work? Cancel. Oh, screw it. It's just going to delete my work. No, it's just going to cover everything over the top. Okay, so we're going to go to the side. Where's the Newman projection in this? Those people that went through the lab, this should be easy. It's a joke. There's a Newman projection you can cite here and technically over there. Okay? So I could go through over here and say point in front carbon number 4, okay, and point in front carbon number 2. Carbon number 4 and 2 are technically in the same space. Okay? This comes from familiarity with the three-dimensional model. Okay? Carbon number 1 is now behind carbon number 2. Carbon number 5 is behind carbon number 4. Where's carbon number 3? Okay? And you can go through and say left and right, and I'm okay with that, but I actually don't want left and right. I want up and down. I want up and down relative to carbons 2, 4, 1, and 5. Carbon number 3 is up from those lines. Okay? For the record, because the recording doesn't hold any of this, when I asked that question, pretty sure you all stonewalled me real hard on that, of like, what the hell are you possibly asking? There's no way you can see that from that drawing. Okay? And I would agree probably the vast majority of you did not. Except one person in the classroom was like, it's up. Why'd you say it was up?
I have the model built.
I mean, if you build the model, that takes all the fun out of it. Yeah, that's where it comes from, being able to manipulate and understand what's happening with the model. You can do it with the drawing. How easy was it to see that carbon 3 is above those atoms? Okay? If you can see it, you're really lucky. Okay? Most people cannot see that. Where's carbon number 6?
Above 5 and 1.
It's below 5 and 1. You're like, but it's up there. No. The orientation of where those angles are and what they mean in that three-dimensional space becomes really challenging to go through and see. Okay? This is why I would encourage you to take advantage of the model kit. Okay? Our two Newman projections are fused to each other. 3 and 6 connect the two Newman projections. We can then continue out the rest of our Newman projection drawing. That's why it looked weird. Well, it looks weird for lots of reasons. Okay? But the less symmetric you are with your drawings, the more weird it's going to look. Okay? What we've now shown are all the bonds all the way around on the outside. 3 and 6 I chose to be in the middle. Okay? Why did I choose to look down the 1-2 bond and the 4-5 bond? Why not look down the 5-6 and the 3-2? Or really any other angle? What were you going to suggest before I talked over you?
The axial position.
No.
Or maybe like the
I'm picking a viewpoint that allows me to see the substituents in the Newman projection. If I picked a Newman projection where carbon 2 was where carbon 3 was drawn here, that's now not in the Newman projection itself. That's off to the side. That's not going to allow me to see any of the energetics that I need to go through and see. Okay? So, to sort of maybe kind of help.
So we were able to decide that the chair with the second methyl group on 2 being EQ, what is it?
Yeah, we just said EQ.
That's just like the most optimal or lowest energy.
Yeah, why is it the lowest energy? That's an interesting question. Let's see if we can come back to why it's the lowest energy. So what we've done here, okay, is I made a blanket statement. Equatorial is more stable than axial. Why is it more stable? There's rules behind why it's more stable. What time is it? When is class over?
45.
I am so sorry. I did not see that at all. Okay? You are welcome to stick around until I answer this question, or you can take off. I apologize. Really? Okay, sorry. There's our chair. Everybody see the chair? We'll try and spin this as fast as I can. Nobody has anything else to do? Like we're done, right? Okay, just
we've got our head with the methyl, and that methyl equatorial. Everybody kind of good? All right. And then what I said we wanted to do is change our viewpoint to look down the 1, 2 spot. So there's the 1, 2. Oh, where's my 4, 5? There's my 4, 5. Okay, that's nice when I see that. We go, oh yeah, I see that. Doesn't always happen. You see where I'm holding? Where I'm holding is your Newman projection. Okay? The 2 Newman projections. Okay? And that's where we now want to kind of sit with our question on deciding where our Newman projection stuff is. Okay? We go through and look at our label. 1, 2, we have 2 equatorials, or sorry, 2 methyls on position 1. So here's position 1 at the back. Guess what this line is up here?
CH3.
That's my red CH3 that I said was equatorial in my drawing. Sorry, what's the word? Axial?
It's sort of an A.
I should just go home. Position 1 down here. That now needs to be our equatorial. And then at position 2, we have that purple methyl. There. So to answer this question, how many Gauss interactions are present in the most stable chair conformation? Well, we've established this was the most stable chair conformation ultimately because we cheated. We just said equatorial was more stable, so we tried to put our substituents in as many of the most stable positions as possible, our equatorial. Okay? If you don't know, that's okay. What you can do is do the other chair and run this exact same process, but do the chair flip, where 2 of them are axial and 1 is equatorial, and see what happens to the number of interactions in each. Okay? So now that we're in a Newman projection, we can start to have this conversation about our Gauss. And they ask anti? Or just Gauss? Oh, diaxials. Okay. So what do we see in here? Well, there's nothing there, but yeah. What do you see? We're seeing the Gauss interaction. That red methyl is hitting that purple methyl in a Gauss interaction. What do we see here? That purple methyl is hitting the orange methyl in a Gauss interaction. Okay? Everything else, or all those other lines that we went and drew on there, were all hydrogens. So we could tag those in there if we really wanted to. Okay? And we get super excited about it and be like, yay, we've got it figured out. I'm going to go through and say that there are 2 Gauss interactions. And I keep forgetting. It said anti? My drawing's over the anti. Diaxial, sorry. Okay. Oh, sweet mother. Okay, so. We go through and say we have 2 Gauss interactions. Should we have any diaxial interactions? Diaxial meant there were 2 axials talking to each other. Do we have 2 axials? We really just have that 1 methyl. I would argue there would be no axial interactions or diaxial interactions. Okay? And so we'd go through and we'd say 2 Gauss and we'd say no diaxial and we would get wrong. Damn. Okay? Well, what did we miss? Right? We got our structure. We put the 2 in front, so there's my first finger to that finger, and then that finger to that finger, yeah? And there's our 2 Newman projections. We're getting the exact same thing, aren't we? What's right here? If you're like, you're pointing an empty space above a model kit, okay. Let's do blue. What's right here?
You mean the groups can have interactions with the ring? Yes. Did you count them? No. Which means you got to count that. Okay? So there's another Gauss interaction. So we go, okay, I get it. I missed one. That's fine. 3. Nope, wrong. But wait, there's more. Where's the 4th?
And the orange one.
Okay, the orange one. Okay, which we're just going to color it in here. We're going to say the orange one is down here. We're missing that gauche. This is time to throw a flag. As in, that's wrong. Why is that wrong? What's it gauche to? A hydrogen. Do we count gauche to hydrogen? Nope. That's not the 4th. You guys ready? Okay. We got it, right? We've got the Newman projection on lock. Nothing could confuse us. We've got it. What did I just do? And for the record, if you weren't watching, that was my hands, all hands. Okay? We'll revert, because we said we wanted to look down the 2-1 bond. Is this atom number 2? No, that's atom number 1. This is what we've been looking at for all our gauche interactions, right? Okay? Looked at the Newman projection so we could see it clearly when we did a great job identifying that Newman projection. And now watch again real carefully. What am I doing? What did we just identify? You mean there's a different Newman projection I could look down? And when I look down that different Newman projection, I can see a new interaction appear? Yeah. Yeah, I can. Right? So when you're going through and looking at these projections and trying to count these interactions, you have to be real careful that you don't count just the interactions on one Newman projection, because there are others. Right? And the lesson that you're going to find out of this is that every axial, okay, and I'm just going to tell you the answer. I'm not sure I wanted to erase that picture. How do you spell every? Close enough. Every axial position has 2 Gauss interactions with the ring. That blue spot was the Gauss interaction with the ring. Okay? So that red methyl, yes, has that blue Gauss interaction, but then when I shift and look at a different Newman projection, it's going to be Gauss to a different atom within the ring. Okay? So for this configuration, that red methyl is going to produce 2 Gauss interactions. Okay, 2 blue Gauss interactions. We still have the green interactions. Those still count, so we're going to get up to 4. Are those purple and orange methyls also going to generate Gauss interactions with the ring? Say again? Statement says every axial generates Gauss interactions. What's special about our purple and our orange? They're equatorial. They're more stable because what interaction do they generate with the ring? You're not wrong, but as a no interaction, we name it. What's the no interaction we name? Here's my methyl, okay, back here, interacting with an atom of the ring via my Newman projection. What is that interaction between my hands? And sometimes this can help. Anti. That is an anti-alignment. Every equatorial will generate anti-interactions with the ring. Okay? And they are effectively no interaction, which is why we don't tend to count them. Okay? Is it going to generate just one? It's also going to generate a second anti-interaction. So when you're looking at a ring, we're talking about Newman projections, every bond gives you the potential for a Newman projection. Within our ring structures, we have to account for those properly and account the other angle behind it. What you should go through and do with this one, and we'll kind of end it here, is chair flip it. And if you don't know what chair flip is, that's because you haven't done lab yet. Okay? After lab, you should know what a chair flip is and how to do it. Chair flip it and count your Gauss interactions again. What you will discover is you're going to get significantly more Gauss interactions the more axial positions you've got. So one of the reasons why our equatorial is so much more stable than our axials. With that, we are done.